我到目前为止，我想我们大概都还在复习一些基本的观念或者基本的这个数学技巧。我们来看一下如何把刚刚学的东西用到这个 wave equation 里头来。Okay, well the whole purpose is that we don't want to deal with the time dependent part. Okay, for some electric field or magnetic field, there's time dependence and also position dependence. Basically, we want to convert this into something that is only position dependent. We want to take out this dependence because this dependence is always given by ER multiplied with exponential j omega t. Okay, we want to take out this part and only deal with the calculation for this part. That's why we create a Phasor. Okay, so let me just use one example to sort of tell you how to do Phasor calculation. Well, suppose that you have some amplitude. This amplitude is a function of time and also the position and also some phase. Okay, so definitely you can create a Phasor from this amplitude. When you write this into this dependence complex exponential j omega t, this means that you are dealing with time harmonic field. OK， 在这门课里头呢，我们都是用 sin cosine 来表示一个波，所以呢，这是一个 time harmonic field. So if you take a differentiation of it, then you drop j omega in front of this Phasor. OK, so for this real world amplitude wave equation, this psi is a real number. Okay, want to create an expression that only deal with the Phasor. So in this expression, you have double derivative of psi with respect to time 2 times. So you drop j omega square in front of it, and then change this psi into psi hat. 当你从这里写到这里来的时候，你注意到它的这个符号的改变。这上头没有帽子，这里多了一个帽子。Okay, that's how you convert a real parameter expression into a Phasor expression, right? Whenever you encounter, whenever you have the temporal derivative, you just drop j omega into the expression, and then convert this real number into Phasor. Okay. So now you have omega divided by u. You have omega divided by u. But you know this omega is 2 pi frequency. U is equal to wavelength multiplied with frequency. So you end up having a term that is 2 pi over wavelength. And then this k is defined to be 2 pi over wavelength. Okay, so you have a new equation with the Phasor amplitude as a variable, and then now you have plus k squared. This k is equal to 2 pi divided by the wavelength. Okay, so you don't want to now you don't have to deal with 2 differentiations. You only deal with one temporal one spatial differentiation, one spatial differentiation. 原来这个式子 you have to deal with the differentiation of space and time. Now in this Phasor expression, you only have to deal with one differentiation with respect to the position. Okay, so this is a sort of simplify your calculation. And there's a name associated with this equation. We call this Helmoltz equation. Okay, And this equation is often used as a starting equation for time harmonic electromagnetic waves. Well, be careful that when you use this equation is only valid when you assume it's a time harmonic field. Okay, this is how you reduce this wave equation into Helmoltz equation. You assume this amplitude as a time harmonic variable. Okay, don't forget the basic assumption for you to reach this Helmoltz equation. Okay, 只有 time harmonic field 你有办法把它写成 Phasor 的 notation. Okay. Now let me give you one example. Actually, two examples, and you should be quite familiar with this if you took the circuit theory course before. And 在这个班里头，有没有人没有修过电路学？你如果修过电路学的话呢，你很熟悉这个 RC circuit. Actually, you saw this in the physics, basic physics course. If you have an RC circuit, and then you drive this RC circuit with a time harmonic source, like this, Vs, you can describe this time harmonic source into a phasor multiplied with exponential j omega t, and then the voltage rise on the right hand side, 这是电压升上来 is equal to the voltage drop RIT plus the charge on this capacitor divided by the capacitance. And this is the basic RC circuit. And this charge is the integration of the current. Now, I want to convert this into a Phasor equation. 这是实际的这个真实世界里头的电路的写法。但是呢，在计算上头 it can be much simplified if you convert this into this Phasor expression. Well, to convert it, well, just check this expression. You found that there's an integration of something with respect to time. So just drop j omega into the denominator, and then you can take out this integration. Okay, and then on the right hand side, now it's a Phasor. On the left hand side is also a Phasor of the current. So you can relate the Phasor of the current to the voltage of the Phasor, and then very quickly you derive the solution for the Phasor of the current. Right? 所以这是很简单的这个 very simple algebra. You can calculate. Well, this is not the real world parameter you can use. In order to convert it back to the real world current, then you simply multiply this Phasor with exponential j omega t, and then take a real part of it to get your final solution. So you can see how powerful this technique is. Basically, you take out this dependence, because this dependence is everywhere. So you don't have to put this into your calculation. Just take it out, and then finally you put it back, and then take a real part of it to get your final solution. The same thing, you also do the same calculation for electromagnetic wave, okay, or transmission line variables. So this is just one very simple but quite powerful example to tell you that in your calculation you can just take out this exponential j omega t, and then finally once you get your answer, then you put it back. Okay. And another familiar example to you is that you have a RL circuit, right? And it's very easy for you to write down this the voltage over this loop by using so-called Kirchhoff's voltage law. So this is a voltage rise, this is voltage drop, this is a voltage drop. So voltage rise equal to the voltage drop, right? On the right hand side, this is the source. And then on the left hand side, you have Ri according to Ohm's law. And then this voltage drop over this conductance, this inductance is equal to L di dt. Now you want to convert this. You want to convert this expression into a Phasor notation, and then solve for the current inside this loop. Well, now you take a look at that this expression and found that you have a differentiation of the current with respect to time. So according to the rule, this operator can be replaced by j omega right here. Okay, and then now you write everything into Phasor. This V 加一个帽子 I 加一个帽子，然后呢 you don't have to specifically deal with exponential j omega t. And so it becomes a very simple algebra that you can calculate the current equal to the Phasor of source divided by this term. And if you want to convert this Phasor current back to the real current, you multiply this Phasor current with exponential j omega t, and then take real part of it, and you're done. You're done with it. Okay, so this sort of tell you how powerful this technique is. 所以呢，这等于是帮各位准备一下一点数学的技巧跟数学的 background. Any question? 没有问题。If no question, we're going to move into chapter 2. Well, chapter 2 is all about transmission line. Because a transmission line can be dealt with voltage and current. So I sort of pull forward this chapter and then sort of you can follow the circuit theory you learn from your circuit theory course, and then sort of borrow the concept into this transmission line. But in your textbook, basically is sort of section 9.3 of DK Chen's textbook. Okay, so if you want to read the textbook, you can just check this textbook or the reference book I give you. Okay. 所以呢，我们会花大概2个礼拜时间，或甚至3个礼拜时间来教 transmission line. Now, transmission line is basically sort of some a line transmitting electromagnetic energy. Okay, you want to deliver energy from one point to another point somewhere far away. And then you need to sort of design some sort of transmission system. And so the simplest way to describe a transmission line is that it's a line transmitting an electromagnetic wave. Okay, but this wave can be described by voltage and current inside it. All right. The most common transmission line is basically a coaxial cable, 同轴电缆. Now, for this coaxial cable, basically you have a piece of copper wire at the center, and then insulated here, and then you have another layer of conductor outside, sort of confining the electromagnetic energy inside. And in order not to touch the conductor outside this transmission line, very often that you put some insulator, some kind of plastic material outside to avoid touching the outside conductor. And the electromagnetic energy basically is guided inside this coaxial cable. Okay, 所以这是最简单的一个 transmission line 的结构。这是通常是金属copper， 然后呢 insulator 绝缘的物质，然后外头呢就是又是金属。Okay. So today I took 2 cables from my lab, and you can sort of actually see the structure of these cables. So if you wish, you can just pass around and see the structure. For different diameter, you have different bandwidths for the wire. So you can take a look, especially this end. And feel that it's a piece of transmission line for transmitting the electromagnetic energy. So this is the most common transmission line, but sometimes if you deal with very high power electromagnetic wave, you do use the large waveguide, something like this. And this is sort of some kind of waveguide structure. 它就像一个 pipe 一样，像一个水管一样， 然后呢there's a hollow structure inside. And then electromagnetic wave can propagate. For example, this is a microwave source, a big microwave source producing megawatt level radiation. And then you connect it with a hollow waveguide from one end to some application you want. Okay, so the transmission line can be actually quite big, with some hollow structure inside, and then the electromagnetic wave will propagate inside. And I found that there's animation on the web, so let me sort of, let me see if it will work. I'm not sure it's connected, but okay.我们看一下那个Wikipedia 上头的一个 animation. So this is a sort of cross-section view of the waveguide, and then you have electromagnetic energy guided inside. It's propagating forward, okay, and so you can deliver the electromagnetic energy from one end to the other end, but very similar to a water pipe. If you have discontinuity here, some energy will be reflected back. Okay, so for transmission line, you have to deal with the forward propagating energy and also the backward propagating energy. Okay, so and this will complicate the calculation. Okay, and the reflected power sometimes can damage your source, so you have to do so-called impedance matching. Therefore, you can sort of deliver energy from one position to the other position. And without much reflection back, okay. 所以这个是 transmission line 最基本的概念。所以现在呢，你可以感受到一个 transmission line, it could be a coaxial cable, it could be a hollow waveguide, and very often that you have to drive it. But in fact, it's not just very often. You need to have a driver for that. So you connect a source to this transmission line, okay, and send some energy into this transmission line. For this source, there's always some generated impedance, okay? And at the end, you have your application. And one possible application is that you put an antenna at the end of your transmission line, therefore you produce radiation. So in addition to this transmission line, a whole system, in fact, will include a generator and a load in your line. And if you don't do good impedance matching, then the energy will reflect it back. It's not going to be delivered forward. Okay, and how is this different from the circuit you know about? 这个跟你所熟悉的这个电路有什么不一样？不一样的是，这里是波 ，there's wave propagating inside. It's not just a sort of DC voltage or DC current. So the dimension of this transmission line is going to be much longer than the wavelengths you operate. Okay, so transmission line, if you have to deal with wave inside, this means that the circuit is much larger than the wavelength. 所以如果有一条线，如果我的波长 ，if I have a wavelength this big, then the voltage here and here are about the same. If this is my wavelength, and if this is my line, so if the wavelength is much larger than the length of my circuit, then the voltage here and here are about the same. Here were also about the same. So I don't have to deal with I don't have to deal with a wave. Okay, but now if I have a wave like this, the wavelength is sort of shorter than the length of the transmission line. Well, definitely your V1 is not going to be equal to V2 here and here. And then we have to treat this energy as a wave inside this line. Okay. So this tells you the difference between the circuit theory you run and the transmission line you are going to run. OK， 因为波长变短了，跟你这个 transmission line 的这个长度比起来变短比较短的话呢，你这上头每一点的电压都不一样，都是波的形式在处理。Well, so how does this method the energy delivery? Well, if this the dimension of the circuit is much larger than the wavelength, then you have to deal with the interference of the wave. Okay, you have to deal with the interference of the wave, and this is going to influence the energy delivery along this line, and phase is important. 相位变得重要了。在这里呢，刚刚这个很长的这个电磁波的状况之下，这里跟这里的虽然是不同相位，但是这里跟这里的电压几乎一模一样。Okay, so phase is not important if the wavelength is much longer than the transmission line. But if the wavelength is only a fraction of the transmission line length, then you have to deal with the phase. OK， 所以干涉变得很重要。那譬如说 ，if you have a constructed interference along one direction, then the energy can be delivered into the location you want. But if you have a destructive interference at a certain point, this means that the energy is going to be rejected from that point. Okay, and this is sort of very universal concept that for energy delivery. If you want to deliver energy forward with some element in between, then you want to have constructed interference when you deliver the energy into that element. Then energy can propagate forward. Otherwise, the energy will just reflect back. OK， 所以这是 transmission line 的基本的概念。有没有问题？很清楚的概念。再下来呢，就是比较复杂的一点点计算。所以这概念清楚了 ，right？ OK， let's look at this circuit. So we want to borrow some technique from the old circuit theory. Well, I just told you that the basic difference is that when the wavelength is much longer than the length of the line, then we don't need to deal with a wave. So let's just focus on a small point right here. 我们都只看这么一小段的话 we don't deal with the voltage here and here, but we just deal with a voltage at this point, V, Z, and this point, V, Z plus small delta Z. Then, for this small section of the transmission line, in fact, we can just apply the old circuit theory to this small section of transmission line, right? And we call this lump circuit model. Previously, in the circuit theory, you always deal with lump circuit. So a lump circuit is this. So we just cut a small piece of the transmission line and try to use a lump circuit model to calculate it. But don't forget that this voltage and this current is both function of position and time. So at this point, you have voltage at Z at time t with a current I, Z, and t as a function of Z and t. And after small differential length delta Z, you have a current right here, Z plus delta Z at the same time. And then this V over this distance, you have V function of Z plus delta Z. OK， 然后呢，我们用这个你在 circuit theory 里头学到那些公式下去算，它们之间的关系是怎么样 ？Okay. Well, how do I put element onto this small section of circuit? Well, it's very straightforward that if you just look at the coaxial cable, 这个它中间有一条芯，所以呢，它有一个电阻 over this delta z. So this resistance is resistance per unit length, all right? 这里的 R is resistance per unit length. 所以这一小段的这个电阻呢是 equal to R multiplied with delta z. And 然后呢，这个transmission line 它是一条中间是一条线，所以呢，你这里呢不会放一个这个电容在这里。如果放个电容在这里的话，这个线就断掉了。Right? So you put the inductance right here. And 中间这条芯跟这个下面这个外头这个结构。Okay, think about this. 在这条芯上头的话呢，你是接电阻接电感，但是呢，这两个导体它的效应呢相当于一个电容 ，right？ 因为这个是断掉的，相当于一个电容。So you add a capacitor right here. Okay, but sometimes you have leakage. Sometimes you don't have a perfect insulation between this conductor and this conductor. So you have leakage. So you can connect a conductance. You can put a small value of conductance between these two wires. So this is a very simple and sort of reasonable model for you to start with. Okay. Now let's just use the circuit theory you know about to write down the voltage and current. Want to relate how want to know how this voltage is related to this voltage. Want to know how this current is related to this current. Okay. 那你学过了这个circuit theory， 你最熟悉的就是Kirchhoff's voltage law and Kirchhoff's current law, right? So for Kirchhoff's voltage law, you want to have a loop. So let's just create a loop. Okay, just create a loop right here, and then write down the voltage inside this loop. Okay, so this is the rise of the voltage. Suppose that you have some voltage increased. So the rise of this voltage per unit length is going to be equal to the resistance multiplied with the current on this line, and plus you have the voltage change due to this inductance. And then the voltage associated with the inductance is this term. So this is sort of quite straightforward, except that you have a differentiation of this voltage with respect to the distance, because this R and L are quantities normalized to the distance. 所以在这里呢，这个 RLGC are resistance, inductance, conductance, and capacitance per unit length 每单位长度。Okay, therefore you have a differentiation right here because 这个 R 跟 L 都是每单位长度的一个量。So this is Kirchhoff's voltage law allow you to write down this expression. Now you have a second tool, second law, that is Kirchhoff's current law. So and there's a node. You need to find a node associated with it. 就是电流进来的等于电流出去的，这是 Kirchhoff's current law, right? So let's pick up this point and then apply the law of the current to this point. 所以呢，进来的电流等于出去的电流，所以在这个地方呢， 现在譬如说你电流从这里进来，电流从这里进来，这里流出去，所以你相减之下，这个电流减掉这个电流的话，就相当于这个电流流过来的。So this is also quite straightforward. And the current flowing into this node from this branch of the circuit is that you have to calculate the current going this direction and current going this direction and sum them together. All right. So the first term is going to give you this current. The second term is going to give you this current. And this is just the difference of the current between these two branch and then normalized to per unit length. Because this G and C are defined to be conductance and capacitance per unit length. Okay, so from the round circuit model, you can write down these two expressions. 所以你有了电流的式子，有这个电压的式子了。那这两个式子呢，well, we told that I told you that if this is a time harmonic field, you can always convert these time harmonic quantities into Phasor notation. Okay, for ease of calculation, just try to simplify the calculation. Okay, so for example, this equation, well, this is a spatial derivative, so just keep it there, but convert this into the Phasor. On the right-hand side, you have differentiation of the current with respect to time. So drop J omega right here, and then convert this current into the Phasor notation. That's it. Very simple operation. So the second expression is the same. You keep this spatial derivative, but replace this symbol with the Phasor. On the right-hand side, you have differentiation of voltage with respect to time. Then you drop J omega into this expression, and then replace this V with a Phasor. Okay, so with these two, you can start to do the calculation. 你可以，譬如说，你可以把，譬如说把这个再做一次的这个微分，对 z 再做一次微分。On the right hand side, you will have a term that is di over dz, and put this into this expression. Okay, so you create an expression. You create an expression that is only voltage. So let's try this. This is minus. Let's do two derivative with respect to z, and on the right hand side you have r plus what? J omega L, and then you have di dz. Right? You have this expression. But you know what di dz is. Just put this into this plot, and then you can create one expression that only deal with v. And this is how you get the expression for dv dz, double derivative of v with respect to z, and end up with a v on the right hand side. You can do the same thing for the current. Okay, and these two equations basically are the transmission line equation or the telegrapher's equation. But these two equations are so familiar to you. 这个式子你很熟悉，为什么？ Let's go back to the Helmoltz equation. 啊哈，你看到什么？这个式子。Okay, you compare this transmission line equation with Helmoltz equation. You found that the only difference is that this is gamma square and you have k square here with a plus sign. So if you move this onto this direction, then you have minus gamma square equal to k square. Okay, and this gives you a solution. 你已经知道这个的解。OK， 这个解是什么 ？Let's go back。这个解呢是这个样子。You have a solution for the Helmoltz equation that is zt equal to some amplitude and then cosine omega t minus kz plus some phi. I told you that we have a definition of k like this, right? So this omega over u is equal to k. So we can safely say that the solution is like this. Okay. So now, if you want to construct the solution, for this expression, then you have to replace this with square root of minus gamma square. Okay, but at this moment, we do not know what gamma is. Gamma could be a complex number. Okay, so it's better to deal with the complex notation. So let's convert this back to complex notation. That is Phasor notation, only a function of z. So this is sort of some amplitude in front, and then this is exponential minus j k z, and there could be some initial phase. So if I want to construct the solution of this, I'm going to have v or I that is equal to some amplitude in front multiplied with exponential gamma z. Okay. We do not know what gamma is. Gamma depends on how this calculation will turn out to be. OK， 那我基本上要告诉你，就是说 Helmoltz Equation 给你这么一个解，所以呢，你可以从这个解呢去找出这个式子的解。这里头不一样的地方是 gamma square is minus k square. OK, but for k, there's a well-defined reference because we always deal with the real number of k. But now this gamma can be a complex number. Okay, can be a complex number. So, so let's write down this kind of solution, but the wave could be propagating in the positive z direction or negative z direction. 它可能在各个方向都这个前后都有。So you have to keep this sign. So you have two possible solutions. One is the z propagating wave propagating in the positive z direction. With positive z direction propagation, you have minus sign here. Just like you have a minus sign here for wave propagating in the positive z direction. Okay, and for a backward propagating wave, you have plus gamma z in your expression. But this gamma could be a real number, could be a complex number. Okay, and what does it mean for a complex number gamma? Let's take a look. 这 gamma 可能是有 real number 在里头，有 complex number 在里头。General solution look like this. This is a forward propagation wave. This is a backward propagation wave. And suppose that you just put alpha plus j beta into this gamma, and you end up having this expression. Well, this expression is going to give you give you some attenuation or amplification. OK， 我们来看一下这个，如果说 let's just pick up one solution. OK， minus j beta z minus alpha z. If I have a voltage or current proportional to this term, and then I want to see how the real parameter will change. How do I do it? For example, if I want to construct the real time, the real world voltage as a function of t and z, then I take a real part of v, the phasor, multiply with exponential j omega t. Okay, and suppose that there could be some arbitrary phase associated with that. Okay, so let's do this calculation. 我们现在要把这个 phasor 这种形式的解的 phasor 变成实际的这个真实世界里头的电压。We do this. Okay, everybody is familiar with it. Right, just multiply the whole thing, the phasor, with exponential j omega t. Then it becomes this is decomposed into minus alpha z multiplied with minus j beta z plus j phi 0. This term is not affected by this operator, so you can just pull it out. So you have exponential minus alpha z, just take it out, and then you have cosine omega t due to this term minus beta z, and then plus phi 0. Okay. So it tells you that there's wave propagating in the z direction, but this wave is attenuated by this term. Okay, so you end up having a wave like this. If I plot it over z, and the attenuation is due to this term right here. So it tells you that if there's a real number associated with this gamma, the wave actually attenuates. Okay, due to the ohmic loss of this R and G. OK， 所以这个概念你要了解到，就是如果说你的 gamma 是一个负数的话呢，这实数部分所代表的就是它在这个波呢越来越小。红色的部分是如果说没有 alpha 的话，那这个波的 amplitude remain the same over some distance, but with alpha, then this wave is going to attenuate like this. And in this expression, beta is called a phase constant or propagation constant of the voltage or current, and alpha is called the attenuation constant, okay, or loss constant sometimes. 了解吗? Okay, so be careful that for this transmission line equation, it describes the voltage and the current, and this gamma, it could be a complex number, all right? And especially the real part of it is quite damaging to the wave propagation because there's attenuation associated with it. And in fact, you can tell where the attenuation from is due to R and G. If you take out R and G, you only have complex. You only have imaginary parts. 你如果把 RG 拿掉的话，你只有这个复数部分。Okay, so this R and G give you the alpha, the attenuation of this wave. Okay, any question? 有没有问题？